No,
They were
although
they were not a carbon based.
Oh, they were silicon. Yeah, silicon based. Yeah, that's been a hypothesis because silicon. What group element is silicon? You guys remember back to chemistry? We talked about groups and periods.
No, but I had the chart.
You have the chart, the periodic table. So silicon sits right underneath carbon. So silicon is in a different period, right? But it's in the same group as carbon. It's a group 4. And that means what?
It's related.
It has the same number of valence electrons, right? So it has 4 valence electrons. So it can engage in some similar, there's some similar chemistry there. The bonds are very different. The energy of the chemical bonds with silicon is very different from carbon, but in principle, it can have 4 bonds like we see with carbon, and so it might be able to act as a kind of backbone atom like carbon under some conditions that we're not aware of, maybe. So it's been hypothesized for a while that perhaps there is some life out there on some world where the conditions are very different from ours, where silicon might actually be the backbone, like carbon is the backbone for. Yeah.
That dumbass movie was actually based in.
So there is, it's been around for a while. Yeah. We've never seen it. We don't know what the conditions might be, but that's one of the hypotheses is that perhaps silicon in certain environments acts like carbon because it is has 4 valence electrons like carbon and can engage in some similar chemistry. The bonds, the energy of the chemical bonds are very different from carbon, and they're not as flexible, so there are definitely some problems with that, but there you go. Okay, so before we get going in with orientation at 9, I just wanted to start talking about electrical entries a little bit. And so to understand electrical entries, we just need to harken back to the kinematics, the physics we talked about earlier in the week. So just remember, we talked about forces, right? I said kind of the ultimate law when it comes to this, if you will, is Newton's second law of motion, right? Which starts at force equals dp dt. That's d is just a little d. It's a calculus term. Just think of it as a tiny little change, right? Like a delta, right? So change in momentum over time, right? So forces cause momentum to change. And then we said, well, what is momentum? Well, momentum is a product of mass and velocity, right? So forces equal d, little change in mass times velocity with respect to time. And then we said, well, does mass change? No, it doesn't. So we can just pull mass out of that. And that gives us force equals mass times dv dt, change in velocity with respect to time. And then we said, well, what is the d, the derivative, or the change in velocity? That's nothing more than, when velocity changes, what is that called? That's called acceleration, F equals ma. Okay, now with electricity, we're going to start with something else. It is related to this as far as transfer forces, but the actual, the magnitude of the force in electricity is described by another law, something known as Coulomb's law. And Coulomb's law says that force, right, when we're talking about electrical forces, force equals some little constant k. This is just a constant. It's just a number that makes all the math work out. That's all it is, k. This is called Coulomb's constant. And then Q1 multiplied by Q2 divided by R squared, right? So let's just digest this. Q1 and Q2 are charges. Remember, electricity is electrical charge. Fundamentally, it's the movement of charged particles around, right? Right? When typically electrons move from one place to another, right? That's what we call a current, right? And that flow of electrons is typically what we call electricity. So if I have a bunch of charge in one location, I can call that Q1. Q just means charge. And then if I have a bunch of charge in another location, I can call that Q2, right? So I have a charge here and a charge here, right? And how much charge I have here and how much charge I have here, I multiply those values, right? And then I divide that value by r. R is just a radial distance. Essentially, it's the distance from the center of those blobs of charge, right? So how far are the charges away from each other, right? So how much charge do I have and how far are they away from each other? Those are the two big things that go into figuring out the force that is exerted between these two charges. Now, how many types of electrical charge do we have? Don't make it hard.
Talking about like DC, AC, DC.
No, that AC and DC is how current flows, right? We talked about that earlier in class, right? Alternating current, direct current.
What'd you
Talking
say
about
now?
volts.
I'm talking about charge.
Positive, negative?
Positive and negative, right? Two types of charge, a positive electrical charge and a negative electrical charge, right? Electrons are negatively charged, right? And then when you take atoms and you take electrons away from them, they become positively charged. Protons, right? Protons are positively charged, for example. So if I have a bunch of positive charge and a bunch of negative charge, we know that in nature opposites attract, right? So the positive charge and the negative charge will be attracted to each other. You can see the arrows coming together, right? And the r is the distance between them. Now, so we call that attraction, but if I have two of the same type of charge, so I have a bunch of negative charge here and a bunch of negative charge here, they will be repulsed, right? The force will be repulsive in this case, and the force will be attractive in the other case. And this makes sense because it is this attractive force, right? The attraction between positive and negative charges, which helps produce certain molecules. Remember, in pathophysiology, we talked about certain types of chemical bonding. We talked about ionic bonding, and that is when a negatively charged, an anion bonds to a positively charged or a cation, right? So positively charged sodium would bind to negatively charged chlorine or chloride, right? And that produces an ionic bond, and that's what we see here, that attraction. Now, with electricity, however, it is almost always going to be the repulsive case that we're going to talk about. So are you guys okay so far? All right, cool. So to understand this flow of electrons, I'm going to use what's called a fluid analogy, right? Because we can roughly look at the electrical currents and the such, and we can kind of imagine electricity as a kind of fluid. Think of electricity as water, all right? So I've drawn a picture here. So what I have is I have a dam. Imagine that there's a dam, and I have a bunch of water behind that dam. You guys okay with that? That there? So I have a bunch of water behind that dam, big collection of water, and then down here I have much less water outside of the dam. So far, so good. Now, if I were to put a little pipe through the dam here, or drill a hole through the dam, well, what's going to happen to the water in the dam? What's it going to do? It's going to flow through that hole, right? It's going to flow to areas of low water concentration, if you will, right? So all this water collection here in the dam is producing pressure, right? And this is obviously just potential energy, right? You just have a big collection of water, that's potential energy, right? Now, likewise, if I were to take a large collection of electrons and I have a bunch of electrons kind of close to each other, are those electrons, do they want to come together or do they want to go apart? They want to repel, right? Because they all have the same charge. They're repulsive. So I could take something like a battery, and essentially all a battery is a big collection of electrons, right? A battery. It's kind of like a dam, and those electrons want to get out, right? And so what happens is, in the dam, the water flows through the pipe, and that flow through the pipe, right, that flow of fluid in electricity is called current. Current is a flow of electrons. Does that make sense? And the difference, the pressure difference, the difference between the pressure here in the dam and the pressure here outside of the dam, in fluid dynamics we call that driving pressure, right? And the larger the difference, the faster the flow of fluid's going to be. Does that make sense? Now in electricity, that difference between this collection of negative charge and this collection, so a collection of negative charge inside a battery versus outside a battery, that difference is not pressure, but is a kind of pressure. It is called voltage. Okay, voltage is a form of potential energy. Does that make sense? So when we talk about voltage, we're talking about the difference between one collection of charge and another collection of charge, right? Like a 9-volt battery, right? What creates that voltage is I have a large collection of electrons in one area of the battery and not so many electrons in the other area of the battery. And if I take a wire from one end of that battery and bring it around to the other end of the battery, those electrons are going to flow through that wire, right? Just like the water is flowing through this pipe in the dam. And it's flowing from high water concentration to low water concentration. That's the potential. That makes sense? So far? Okay, cool. So this is potential energy. The actual flow of water is a kinetic energy, is it right? So the potential energy of all that water backed up behind the dam gets converted to kinetic energy. Just like in a battery, the potential energy of all those electrons stored in that battery can get converted to kinetic energy as electrons flow out of the battery. Does that kind of make sense? You can see the analogy. And then the last thing is this pipe here, right? If this pipe is very large, the diameter of the pipe is very large, more water can flow through it, right? Does that make sense?
That's your resistance.
And that's the resistance. And then if the pipe is very narrow, well, what happens?
Resistance increases.
Resistance increases and the flow slows down. So current, the actual flow, is what we care about in electricity, right? In electrical injuries. It's the actual amount of current that flows through the body. That's the problem. Now, can you have a situation where you can have a massively high voltage and very little current? Yeah, you have a lot of resistance. Does that kind of make sense? And that kind of explains why you guys are familiar with tasers, right? And they say that taser is a high voltage, like 10, 20, 30,000 volts. And you think, well, wait a minute. That should just instantly kill somebody, right?
Yeah, it's only like 0.05 amps.
Exactly. So the actual current produced is very small, right? Because there's so much resistance, because those wires are tiny. So yeah, the voltage is really high, but it doesn't matter, right? I could have all the water in the world behind a dam, and if it's just a tiny little crack in the dam and then water's just dripping out, well, what does it matter, right? But then if I have a big pipe and the water's flowing out very quickly, the same thing with electrical circuits. Does that, you guys okay there? So I've got three things. I've got the potential energy, I've got the kinetic energy, and then I've got the resistance. So far so good, right? Or we call potential energy voltage, right? The kinetic energy current, and the diameter of the pipe resistance. Now, the other key thing to understand when it comes to electrical injuries is the following. As a flow of electrons meets resistance, right? So as current meets resistance, you can think of those electrons as kind of bumping into stuff, right? So they're flowing through something, and those electrons are bumping into stuff. And when they bump into stuff, their kinetic energy, right, the energy, the motion that they have, gets transmitted into whatever they bump into. Does that make sense? And it gets transmitted as thermal energy or heat. So as electrons flows through stuff, as they bump into other atoms and molecules within whatever they're flowing through, their kinetic energy gets transferred into those atoms and molecules as heat. Just like here, I could put a little propeller inside of that pipe, right? And that propeller would have a little shaft that could go to a generator. And as that water flows through, it could spin that propeller around, spin that generator around, and I could generate electricity, right? And we call that hydroelectric power. So I could harness the kinetic energy of that water flowing through the dam to right? I could transform that kinetic energy into another form of kinetic energy, right? Now it's not heat here, typically it's not heat in the case of fluid flowing, but in electricity, with it is electrons flowing, that energy gets transferred as heat. Is that, you guys okay there? And does that kind of make sense? So you guys all have your computers, right? What happens when I open my computer up and I start rendering videos and I start playing video games and I start putting load on that computer and more electrons, right? The current flows, more current flowing through those computers to accommodate those tasks. What happens to the computer? It starts heating up, right? It's heating up because you have more electrons flowing through that computer, right? And those electrons are then bumping into atoms and molecules of the components inside of the computer, and they are transferring their kinetic energy into that computer's heat, right? In the computer, right? And then the fans turn on, right? And you have heat pipes and heat sinks, and like it even happens in your phone, right? Right? If you use your phone a lot, right? The processor begins to heat up because more electrons, more currents flowing through it. Does that make sense? So it should also make sense that when talking about electrical injuries, we should talk about electrical injuries as being a kind of burn, right? A kind of burn injury, because one of the major problems we run into is when current goes through the human body, right? The kinetic energy of that current gets transformed into heat, and heat is delivered in the body, and burns tend to be a substantial side effect or sequelae to exposure to current. Does that kind of make sense? Now there's some other special things that happen in addition to the thermal injury, but burns are a big problem. All right, so when we take these three concepts, right, voltage, current, and resistance, these three concepts all have a relationship. And so I've kind of color-coded this, and you guys see this little triangle I drew here? So the V on the top of that triangle is the voltage. All right. The R on the bottom right is the resistance. All right. And the I on the bottom left is current. These are symbols for R is resistance, V is voltage, and I is current. All right, so far so good? And this relationship between these three concepts is something referred to as Ohm's law. This is Ohm's law. And this is really cool. If you write it like this triangle, this helps you remember the three major formulas of Ohm's law. And the three major formulas are voltage equals, check this out, voltage equals current multiplied by resistance. So V equals current times resistance, or I times R. V equals I times R. So if you know the resistance and you know the current, you can figure out the voltage, right? What the initial potential energy is coming into that. But that's not all, right? Because we can solve for any of these three. Let's say I want to know the current, I. So I is going to equal voltage over resistance. Isn't that cool? I don't know. This is kind of the coolest thing. One of them, right? So I, current, equals voltage divided by resistance, or I equals VR. And then the last thing I can solve for is resistance. And resistance is going to equal what? Voltage divided by current. V divided by I. V divided by I. And these relationships are all known as Ohm's law. This is Ohm's law. So let's just review what each of these concepts, what we call each of these concepts. So current, I, is measured in what? How do we measure the current? and amps, or amperes. Right? And this is the vernacular term amps. Right? So we know a 20 amp circuit, right, is going to have much greater current than a 10 amp circuit. Does that make sense? All right. Resistance is measured in something called an ohm. And voltage is measured in what? Volts. Yeah. Good. Right? Volts. So you got volts, ohms, and amps. Okay. And then the last thing that we need to review to really understand the basics of electrical energy is something called, we'll do this, something referred to as Joule's law. What is a joule? We talked about joules, right? What is a joule? A joule is a measure of what?
Long before that.
Yeah, right. That's why we covered all that kinematic stuff earlier, right? So you can better understand this stuff today. So a joule is what? Remember we talked about this on Tuesday morning. A joule is how we measure what? Transfer of energy, right? A joule is 1 Newton. 1 Newton of force transmitted over a meter, right? 1 Newton meter, right? And Newton of force is the amount of force that it would take to accelerate a 1 kilogram object 1 meter per second, right? So a joule is 1 Newton over a meter, right? And then if you add time to that, we call that power, right? So 1 Newton meter per second would be a watt.